So previously we've looked at local or relative maximum and minimum values of a function, and we know that because these are determined by a neighborhood that we can define and change, there can be many relative maxes and minimums for a given function. But with absolute min or max, or global min or max, we are looking for the highest or the lowest y value on the graph. So you would think this procedure would be very similar to finding relative mins and maxes, because all we're doing is finding the biggest of the relative mins and maxes. And essentially it's the same difference, a couple of extra considerations that we need to consider. So let's look at the graph we have here, and I am going to find the max and min. Now if I don't say absolute, I just say max and min, that's assumed to be the maximum min and max that I'm finding. Alright, so I want to do this first of all on a closed interval, which remember includes the points 1 and 5. So if I look between here and here, I want the highest and the lowest y value on the graph. Well, the highest I can see is 3. The lowest would be right here, and that seems like it's about 1. So let's say that the absolute minimum is 1. The min or max value is the y value, the highest or lowest y value. So you'll notice that our maximum occurred at a critical point where the derivative is 0. We're familiar with looking at critical points when we do relative mins and maxes, so it's the same thing with absolute mins and maxes. The minimum is occurring, though, not at a critical point, but at the end of the interval. Okay? So that's another place we're going to have to look as we consider how to find mins and maxes in general. Alright, the next situation, I have an open interval, which means I don't include the values, the points at 1 and 5. The maximum value of y is still 3. The lowest value of y, you'd probably say it's 1, but the problem is, since this point isn't included, it means that the y value of 1 isn't the lowest point. It's a value of y very, very close to 1. And since we can't definitively define that, we simply say that there's no minimum. So one thing I'd like you to notice is that if you have a continuous function on a closed interval, there is definitely a min or a max, and that's always going to be the case. But if you're dealing with an open interval, there may or may not be a max or a min. Next situation, we're going to look at an open interval including the entire graph. So the highest point, highest y value, if you consider the entire graph, is undefined because the graph goes up endlessly, so there's no max. And the lowest y value would be somewhere there. That's occurring at a critical point. Let's say that's -1. So the absolute min is -1. Finally, I want to look at an open interval between 0 and infinity. The highest value, again, does not exist because the graph goes endlessly high. The lowest y would be close to 0, but again, since we're not including x equals 0, we can't say that it's exactly y equals 0, so there's no min. Alright, so before proceeding, please note that if the interval is open, there may or may not be a max or a min. If the function is continuous on a closed interval, then there definitely will be a min or a max. So the extreme value theorem says that if a function is continuous on a closed interval, then there will be a min or a max, definitely. And where would we look for those points? We would do it similarly to relative mins and maxes. We would look at the critical points, but we also need to look at the endpoints. As we saw in the last example, maxes and mins can occur at the endpoints. So all you need to do is find your critical points and compare your y values at the endpoints and critical points. Alright, here's a function. We have a cubic function, and we're only looking at the interval -2 to 3. It's a closed interval. Alright, so where would the max or mins occur? So the min or maxes would occur at critical points or endpoints. So to get the critical points, I need the derivative. and the derivative is 6x squared minus 6x minus 12. Let's set our derivative to 0. Factor. And so we have critical points at 2 and negative 1. Alright, so now we need to compare the y values of the critical points with the y values of the endpoints. And the biggest y value we get will be the max, and the lowest y value we get will be the min. So if you plug these values of x in, I've done this in advance, we get these values. And so our minimum value is negative 20, occurring when x is 2, and our maximum value is 7, occurring when x is negative 1. Now the procedure with open intervals is pretty much the same. The only difference is that there may or may not be an absolute min or max. So we need to consider that, and when we're checking our endpoints, we're still going to check our y values of our critical points, and then to check the endpoints we're going to have to use limits. Since we're not actually at those points, we're going to have to use limits. So critical points are when the derivative is 0, and if we solve that, we get negative 4 equals 4x cubed. X cubed is negative 1, so x is negative 1. So we need to look at the y value at negative 1, which would be negative 1 to the 4th, which is 1 plus negative 4, negative 3. When we check our endpoints, we will do so with limits. So we'll take the limit going to infinity, since that's the direction, the end direction, and x going to negative infinity. So if you go big to the 4th plus 4 times big, you're going to get big. And similarly here, because you're going to get a negative to the 4th will be very big. Plus 4 times negative will be negative, but the power x to the 4th is going to take over, so this is going to go to infinity. So the lowest y value is negative 3. So the minimum is negative 3, occurring when x is negative 1. And since the y's are infinitely large, there is no max.